Welcome to the GOTO podcast. Each episode covers the brightest and boldest ideas from the world's leading experts in software development. Tune in for practical lessons, compelling theories, and plenty of inspiration. GOTO gathers the brightest minds in the software community to help developers tackle projects today, plan for tomorrow, and create a better future. Stay up to date with the latest in tech through GOTO's top-rated events in cities like Amsterdam, London, Copenhagen, and Chicago, and by subscribing to the GOTO Conference's YouTube channel, where you can find thousands more high-quality dev talks. Learn more at gotopia.tech.
Hello and welcome to this mini-series for GOTO Unscripted called The State of the Art, where we are exploring emerging trends in computing. I'm your host, Charles Humble. I have over 30 years' experience as a programmer, architect and CTO, and I'm currently working mainly as a freelance consultant and advisor, as well as a tech journalist, editor and podcaster. Interest in and investment in AI research has never been higher, but current artificial intelligence systems have adopted a narrow approach which relies on extrinsic learning mechanisms for gradient descent and its variants, serving as the primary means of model optimization. Intelligent systems arriving from biological brains, however, display intrinsic learning through integrated processes. Since biological brains also operate with power and data efficiencies which are otherwise unparalleled and have the capacity for rapid real-time adaptation, it may be beneficial to reconsider neural systems in the current search for AI. I'm joined today by someone who's been exploring this area in detail. Dr. Ewelina Kurtys is a scientist turned entrepreneur pushing the frontier of bio-inspired computing. She graduated in pharmacy and biotechnology in Poland and pursued a PhD in neuroscience in the Netherlands, where she specialized in brain imaging. She continued to work in this field as a postdoc at King's College in London. She has since left academia to work in industry and is currently strategy advisor to FinalSpark. FinalSpark is one of a small handful of companies looking to move AI from digital processes to bioprocesses. That's to say, processes built from living neurons. I'm very much looking forward to this conversation. Ewelina, welcome to the show.
Thank you so much. Very happy to be here.
It's wonderful to have you on. So maybe let's start a little bit with your career journey. What prompted you to move from academia to business, and in particular this focus on small startups?
So that was trial and error. I always wanted to leave academia because I was curious what is outside. What else can you do in life except research? And I also was compelled because I think that in industry you have more options. Like in academia, I believe there is only one way to be successful, which means to become a professor. But in industry, I think there are many ways to become successful, depending on what you want and what is your personality. So I was always intrigued by that. But initially, of course, I thought the best is to work in a big company. But then I realized that to work in a big company, you have to fit. And then I realized that's not for me. And by coincidence, actually, by networking, I was in London at the time, which is perfect place for exploration. And I was networking some people, random people advised me to apply to some small company, which was doing medical imaging. That was also something I was doing during my research, mainly on brain. I thought it's a good starting point because there will be at least one thing which I understand very well. And that indeed gave me advantage to start because everything else was new about working in industry. So at least on the technical side, I had some edge that I understood medical imaging, which is highly technical service. So this is how I started, but then I realized that I prefer much more sales and business development and marketing than being a scientist in industry. I think a scientist in industry is totally different than a scientist in academia, because in academia you have a lot of freedom to do what you want, more or less, but okay, but you have a lot of freedom. It's maybe not a lot of money, but you always have freedom. But in industry, you have to really stick to the agenda. And you cannot follow your really curiosity so much, but you have to do a lot of stuff. Sometimes it's highly technical, actually. So I knew I don't want to be a scientist there. And then, just trial and error, trying different things. I also tried some project management. And, I realized that for me, the best job is when I talk to people, when I have some interaction, when I can explain something. And when I can explore. That was also very important for me, at least. But I think for everyone is different. But yes, that was my move from academia to industry.
Is there anything that links the two areas for you? So are there lessons from being an academic researcher that apply to what you're doing now?
Yes, absolutely. There is always a lot of common links. There is a lot of general skills which you get any job, like reasoning or problem solving or resilience. And in both cases, when you work in a small company and when you work in academia, you have a lot of answer. It's not sure what you do, and a lot of things can change. So I think there are a lot of things in common. I think in general, when you do a PhD, after when you move to industry, you can do practically any job you want. So the rest is just your character. But more or less, you can do everything. Maybe except some highly specific technical jobs, you can do anything. So the rest is just your character and your personal preference.
What was it that drew you specifically to FinalSpark and this idea of biocomputing?
So I always look at the people, not so much the ideas, because ideas can be good or bad. It doesn't really matter, but it's important the people. And what I discovered that actually in deep tech, you have nice people to work with. I have the impression there is such a tendency. And I had the chance to meet the founders of FinalSpark at one of the conferences in London, which was at the time was really eye-opener for me because that was AI Summit. I think now it's getting a little bit boring because every AI discussion is around LLMs, which is solution for everything. A few years ago, before LLMs, we had a big variety. And actually, I came from imaging industry, so image analysis is something what you can do with AI. But then on this summit, I realized that there are many other things you can do and doesn't have to medical image. It doesn't have to be medical image and it doesn't have to be even image at all. So that was really a big revolution for me. But yes, I became interested by FinalSpark because I thought the founders have a nice culture. And indeed, they have very nice team, very nice atmosphere, and everyone is happy there. So I think it's a good place to work. Although I'm always remote, which I also enjoy, because that's actually happened to for me be a perfect match. Remote working for my personality because I really enjoy working from home. I can discipline myself. I can do very well by myself. Of course, it's again not for everyone. Some people feel better in the office, and I think it's very important to remember that is not one solution for everyone. But at least for me, it was perfect because when I met them, I was in UK, in England. I'm still here, and they are in Switzerland. And yeah, it seems to be perfect because I can work remotely. I never have to go to the office. So that was also very nice. So I think it's mostly about the people and the ideas, every idea you can execute good or bad. A lot depends on the daily basis and the atmosphere you have in the lab and the team.
So I said in the intro that the goal of FinalSpark is to build computers using living neurons for AI.
Yes.
So is that a specialized goal like a GPU or something like that? Or is that something more ambitious like a general purpose computing device?
No, it's definitely general purpose computing and it's a very ambitious goal. And we expect to be ready with the computer in 10 years, which is of course an estimation because with such a project, you can never, you cannot have a precise timeline, but we estimate it will take 10 years. Maybe it could be faster because of the LLMs. So again, we come back to the same topic like in every AI discussion today, LLMs, but it's true that they can accelerate research a lot. And we can already see this today in our R&D. That we can set up some automated agent who can write Python scripts for us. And we see this already in real life that AI can accelerate a lot R&D. So who knows, maybe our timeline will be faster. But for now, we estimate 10 years. So it's very ambitious, it's very challenging. And also we are only 6 people, a very small team, because we are self-funded by the founders, Fred Jordan and Martin Kuter. These are 2 Swiss entrepreneurs. They have already another company. And this is why they have money for FinalSpark. But to be really reach the goal in a reasonable time, like 10 years, we need external investments. So we are seeking 50 million Swiss francs, which is a lot of money. But this is the money which would make a difference because for our budget today. And the main objective for the investment is to increase the team. Because, which is not a surprise in such a project like that, in the deep tech, the success depends on the people and on how many people work on the difficult problem. So we are very ambitious, yes, but it's also challenging and long-term idea.
Right, yes. So when I was sort of thinking about this, it seems to me there are sort of two mutually inclusive possibilities. So you could use biological cells as the substrate for information processing and intelligence. And the other option is you could develop new AI algorithms which are inspired by those biological systems.
Yes.
So why specifically are you interested in the first option? Why are you specifically interested in using biological cells for this job?
Because we believe this will be a real revolution. Because you are right, a lot of algorithms can be optimized, and it's already the trend we see in the industry. Absolutely, people are doing this all the time. You can also optimize the hardware. People try to optimize digital hardware. They even sometimes try to make analog hardware so that be closer to the brain. And this can lead to even bigger gains of energy. But we believe that nothing will be so revolutionary like living neurons, because living neurons are 1 million times more energy efficient than digital software hardware we have today. All these improvements which we are doing today are little steps, but living neurons would be a huge step forward to energy efficiency.
And that's really interesting. I mean, that was something that we talked about prior to the recording, and I mentioned it in the intro as well, because it's very much my area. So my sort of consulting work is focused on ways that we might reduce IT's carbon footprint. And obviously, you know, as you said, the energy efficiency of neurons is kind of astonishing. Can you give us a sense? I appreciate it's very early days, but can you give us a sense of kind of what you're expecting to see or what you can see in terms of that efficiency?
Well, 1 million times more efficient. So that will mean, actually, we don't want to change anything for the end user. That's our dream, is to just replace the hardware. So basically, today you use ChatGPT on hardware digital. Tomorrow, you can use it on living neurons. And the only difference for you should be the price. And this is something which is very important, although many people don't appreciate this yet, because today we don't realize how expensive is AI. Why is this? Because running large language models or any other sophisticated AI systems is actually really expensive. And today, a lot of companies are selling this cheaper than it is really cost, because they want to increase the adoption. So, for example, OpenAI, who created ChatGPT, they lost already $19 billion. Mm-hmm. So what does it mean? That means that ChatGPT is much cheaper than it should be to make this company possible to survive. And of course, this is long-term strategy, because they want to work for adoption. They want us first to learn how to use it. And then later, once we appreciate the value of systems like ChatGPT or other LLMs, then they can increase the price, because we will be ready to pay more. And this is really important problem, which we don't see yet because of these lower prices. But in the future, it can become even more serious. Why? Because every better model is consuming more energy. And also because if we use more and more AI, that means also the over demand will be higher. So today, maybe you just need a little subscription for $20, which is around the price for now for ChatGPT. But maybe tomorrow you will automate much more things, much more tasks, because we will learn how to do this. Then even this will increase the price. So the usage is growing, and also the real price of AI is much higher than in reality. So that means that in the future, we can expect very high prices unless some solution will be found to how to make it cheaper. And I'm sure that there will be a lot of small incremental changes on the way, because we see this already. There's a lot of papers on software and hardware on optimization. So we will see a lot of small percentage optimization, but living neurons will bring a revolution. That will be 1 million times more energy efficient. That is huge difference. So yes, so the difference will be in the price. That's what we want people to experience in the future. Not some, we don't really expect to build some different models, because our dream is to match the performance of digital in some tasks, not everything, because of course, living neurons are good for some tasks like maybe generative AI. We conclude this based on how human brain is working. So of course, we don't expect that neurons will replace digital in everything, but in some things it will replace and will be much cheaper. So that will be the result, because everyone is asking for the case studies, everything. So we imagine generative AI, but much cheaper.
Right. Yes. Yeah. I think it's worth saying, I mean, the ways that we're currently doing large language models are incredibly inefficient. And there are absolutely ways that there are techniques that we already know about that we can use to bring the efficiency down and the costs down. We're not doing those, a lot of those things that we're not doing yet, but we can do. But I also completely agree that what you're talking about, if it all works out, could be a huge change in terms of capabilities and efficiency, which I do think is really interesting. I appreciate you're at the very early stages, but can you give us a sense of what your performance expectations are? Because I would have thought that, I mean, I don't really know, but I would imagine biological neurons are going to be an awful lot slower than either silicon or quantum-based systems, say. So kind of, can you give us a sense of that, what the performance is like? Do we know that at all?
Yes, absolutely. You are right. So the performance will be different. We can conclude this, some estimation based on how we see human brain. So we know that the human brain is very efficient in complex tasks, but we know also it's slow, as you are right. And it also has less memory. So we will never, your brain will never remember all the books you have behind you. But like by heart, every page, but a computer can do this, even much more books. So there are significant difference. So that's why we believe living neurons are good for generative AI, for creating ideas, for solving complex problems very efficiently, but not necessarily for high-speed computing, for sure not. So we can expect for sure it will be slower, but how slow, it's difficult to say because today we have only human brain, which is quite small. And what we want to build as a computer will be actually a huge bioserver, which maybe will be even 100 meters long, all from living neurons. So it's hard to predict how fast this structure will be, but we know for sure it will be very efficient.
I had a sort of related question, which is a bit of a computery question, but do our brains work in parallel, or would you expect a biological computer to be, in effect, like a single-threaded processor or handling one task in a kind of linear way? How does that even work?
No, we definitely have parallel computing in the brain. I actually wrote a blog article about this, about the difference between brain and digital. It's on my LinkedIn. So if someone enter my profile, it's one of the featured articles, so it's easy to find. And yes, definitely, parallel computing is also one of the reasons why brain and living neurons are so energy efficient.
How much do we understand about how neurons encode information? I thought that was something we didn't really understand at all.
Yes, that's the biggest challenge actually of this project, I would say, because we know quite a lot how neurons process information, about how the signals are processed by living neurons, but we don't really know a lot about the encoding. And that's really the challenge, because for sure encoding is different. We know that, in computers you have 0 and 1s, and in brain you have time and space. So it matters when and at which point neurons is active, electrically active. And this is totally different encoding, but we don't really know what does it mean. So that means in practice, nobody can read our mind today, because we can detect the signals from the head, but we don't really know what they mean. We can, of course, make some correlations, but we cannot really decode perfectly the signals. So that's actually the biggest challenge of this.
And our brains are also, I think the term is plastic, but basically they kind of change over time. So I'm presuming when you're running experiments in your lab, those experiments can produce identical experiments with the same set of cells or neurons can produce different results on different days.
Yes, you are right. So plasticity is a good thing, of course, because it allows us adaptive learning, which is fantastic. We can learn by experience, step by step every day. But it's also a challenge for experiments because the system, general neurons are not stable system in general. And that means, as you said, that today experiments can give one result, tomorrow can give something different. So this is just another variability in our research, which increases the challenge.
So I'm presuming then when you're running your experiments, you have to have an awful lot of automation because you've got so many unknowns and you need the experiments themselves to be repeatable, right?
Yes, absolutely. So we never report any results if we don't have repetitive, really repeated this several times, because we get a lot of spectacular results, which were just one time or maybe 2 times. That's not enough. And for example, we managed to store 1 bit of information. That's something what we have done many times. We know it's reproducible. So we were basically able to change the state of the neurons in manner of two states, two different states, 0 and 1, which can be mathematically calculated. If we say we've done something, that means we've done this really many times and it's reproducible. And that's actually the biggest challenge. That's why we don't report many of our results, because they are hard to reproduce.
I know mainly from a conversation I had with somebody called Dr. Barbara Oakley, that a lot of neuroscience research papers are not actually reproducible at all.
Yes, absolutely.
So the fact that you have something that is reproducible is itself quite interesting. So is that the main way that you validate your results, or are there other forms of validation that you do?
No, at the moment, reproducibility, I would say, is important. Of course, we have also a lot of methods on how to process the signals. So we make sure that what we get is real. For example, in biological signals, you have a lot of noise, and this is well known. That's why you have to, of course, filter out the noise. So we do a lot of things. Repeatability is, I think, the most important criteria to claim that we have done something.
Right, yes. Is there any consensus amongst neuroscientists as to whether our brains are deterministic or non-deterministic?
Oh, this is a very interesting question, which is definitely, I think, beyond the expertise of FinalSpark. But I read recently a very nice book about this, which is called Determined. And I think it was written by Robert Sapolsky. I have it on my shelf. And I think I have to say this book helped me to change my way of thinking, which is rare because I'm sometimes stubborn. But I have to say that I cannot find the reason to refute the arguments in this book. So far I have to say, I have nothing to say, what I could say to justify why it's not true. So basically what the book says and what is consistent with the current neuroscience is that everything is actually deterministic. It's just that it's so complex that we don't see the cause and effect, which is absolutely normal. And actually, when you look at the human brain, there are a lot of obvious things. Like, for example, our intelligence is shaped also by genetics. I mean, if you are born, for example, with Down syndrome, you can never have IQ 150. This is maybe the most blunt and obvious example, but there are many other subtle examples. How our intelligence or our brain capacity is actually determined by the genetics. And of course, the upraising also matters because there is this vivid discussion always in biology, whether it's more environment or the genes. And of course, I think currently it's quite maybe agreed that it's a interplay between genetics and environment. But, you know, if one cannot go without another. And actually environment, we can also not choose. So you don't choose where you're born and what is your environment, and you don't choose your genetics. And actually, if you really think about this deeply, everything has a cause from the every moment. There is some molecule. If you have this molecule, it's because of your expression of genes. And if you have these genes, it's because of the genetic material you got. So actually everything is determined. So I have to say that I believe now, or maybe I'm actually believe is not a good word in science, but I would say I'm convinced today that indeed everything is determined, definitely determined. Although it's open discussion and many people, you know, is connected to the discussion about free will, which we don't want to accept that we don't have it. But actually, if you follow the reasoning of current neuroscience, that actually there is no free will. We are just determined by the circumstances, which I think is very interesting. And I think unfortunately is true. I cannot find a reason why it wouldn't be true. So yes. And I think also in the brain, everything is determined, definitely. So I don't think it's random. It's just very complex. So the same also what we have in our lab. That's why I believe we can build the computers because it's all controllable, but we just have to find a way how to do this. So yes, I think today, I think that it's determined. Yes. And it's actually not only neuron, but you could say the same about every living cell, because what I said just on the neuron, you can actually say about any kind of living organism, even one cell. So yes, that's what I believe.
That's so interesting. I'm dying to get into talking about the prototypes that you've built and what you're seeing, but I want to ask one more background question. So again, my understanding, this is not my topic area really, but my understanding is that neurons in adult brains live more or less for our lifetimes, or more accurately, if they don't, that's problematic because we don't replace them, right?
Absolutely true. So, although we have some little neurons growing also, yes.
Right. So with your neurons, how long can you keep them alive currently?
Oh, this is a very cool question. Yes, very important, practical. So actually currently around 3 months, although we recently had a success of 7 months in our lab, but this is outlier. Generally it's around 3 months, which is very long for the lab condition. However, it's not very long for a neuron, what is possible, because as you mentioned, of course, they can live even 100 years in our brains. So it's all about how to make the condition of neuron as close as possible to the natural. And this is still a challenge because everything in the lab matters. We, for example, put neurons on electrodes so that we can send them electrical signals and we can receive response. And that's already stressful for them because it's a contact with the artificial material. So the same is about any kind of glass you use, any kind of plastic material you use to keep your neurons. So these are all the challenges and why neurons don't live as long as in our bodies. But we believe this is also engineering challenge. So we believe we can solve it. It's just that today, the biggest challenge is learning in vitro. So how to control the neurons in vitro, how to make them perform some tasks. And for this, 3 months, let's say, is enough for experimenting. And then once we solve this problem of the algorithm, which is very long and a challenging problem, we can think about scaling, and we believe it's possible to solve. Yes.
So presumably then you're keeping the cells in conditions that are very similar to a human brain. So the same physiological conditions, pH, temperature, nutrients, fluids, whatever.
Yes, absolutely. And that's actually what everyone is doing in the lab, everywhere where you keep living neurons or living cells at all, any kind of cells, animal, human, anything. You always try to keep the condition as close as possible in the nature. And pH and temperature, and they always have to be in the liquid. They have to be to get some nutrients to survive, like every living cell.
So can you tell us about the prototypes you've built then? How do they actually work? How are they constructed?
So currently we built a prototype. So we have little round structures of neurons, around 10,000 neurons each. And we put them on electrodes. And we can send them electrical signals and we can measure response. So this is the prototype of the computer. What is very special is that this prototype is available remotely. So we have universities from all over the world who are using it. And we also have industry clients, people who pay us for the access to the lab so that they can do this fundamental research on signal processing on neurons. Of course, this is very fundamental. We cannot yet rent computing power, but we have very robust and very unique tool for studying biocomputing.
And you're using human stem cells to do this?
Yes. So basically we are using stem cells which are derived from the human skin. And this is the procedure which was awarded by Nobel Prize around 15 years ago. And basically you can sample skin cells, you can produce stem cells from that, and then you can produce any cells you want from this, including neurons.
When I was doing the sort of background reading for this podcast, I was reading on the FinalSpark site about brain, again, I might even be mangling the pronunciation here, sorry, but brain organoids or organoids. Can you correct my pronunciation and explain what those are?
No, perfect. So organoids is actually a technical term, how we call these round structures, I told you, which we keep on electrodes. So organoids is something what is meant to be complex and somehow resemble human brain. However, it's very important. It's not the same because we are just using building blocks of the brain. It has nothing to do with the brain. Some people call organoids brain on the dish, but I think it's unnecessary marketing, which is actually hurting the field because when the policy makers will start to believe that we really have brain on the dish, they will start to invent some regulations for that, which I think is really wrong because organoids, of course, they are complex. They are 3D structures. So they can have a few type of neurons or different cells, but that doesn't mean they are brain. So it's far, far away because brain is much more complex, and we will never be able to build something so complex as a human brain. But yes, organoid is 3D structure, and what is specific in organoid is that you have few cells, usually few type of cells, and it somehow can resemble some kind of circuits, which we have also in the brain. So you can, for example, try to combine different type of cells, which you believe could be good for learning.
And how do they form connections?
And naturally, this is just biology. You put neurons in together, and they will just connect if they can. So this is just pure nature, yes. And of course, totally random, they connect, yes. The same actually as our brains start. Yeah.
You said you can basically store one bit of information on a neuron currently, right?
Yes, but this is just an example. I wouldn't say this as an indicator of the memory. I wouldn't say so. I think it's too far. It's just that we were able to have consistently keep two states of the neurons. And in this way, we used something like which is called a center of activity. So basically, neurons are connected to 8 electrodes, and you can mathematically calculate the center based on the activity which is measured from each electrode. So it works the same way like gravity. So you have more activity, then its center is going towards this point. And we were able to move this point, this center of activity. So that's what we did. And that's more like a proof of concept that we can do something. But that's not really how, I believe it's not how the biocomputer will work.
So how are you making them active? Is that neurotransmitters or is that electrical signals, or how does that work?
So actually in a neuron, you can divide two types of signals, is chemical and electrical signal. And actually in biology it's all chemical, but we just make this distinction. For us it's easier because at the end in neuron, everything happens because of the chemistry. Also, when you have electrical signals of neurons, it's at the end the ions, which are plus and minus, and they change the location. And that's why you have electrical something, what is actually changing the voltage, which you can measure as an electrical signal. But yes, we can basically, for simplifying, you can say you have electrical and chemical signals. We use both. So we have developed our lab. We are always improving. We started with electrical signals. So neurons are always on the electrodes. So we send them signals and we receive the response. But now we can also send them chemical signals. So that means we can, for example, release dopamine, which we can use as a reward during some experiments. So that's just example of something we did.
And can you communicate with neurons? I mean, do we know how to program neurons?
Yes, well, when we store one bit of information, that's is communication, because we send them signals, we receive response. We always have bidirectional communication. It just doesn't always work as we want it.
Right. Okay. I'd like to shift and talk a bit about, there are a lot of ethical issues that come up, at least for me, with this. So I'd like, if you're okay with it, to explore some of those a bit. I mean, the first thing that I was thinking about is, how do you get informed consent from donors? Because it's kind of very difficult, I think, for most of us outside of the field to even kind of imagine what you're doing. So how do you go about getting informed consent? Can you get informed consent?
Well, actually, it's very easy because this is process which is already commercialized. So there are companies which are selling stem cells, which are derived from human skin. So that means that everything is already sorted by someone else. And you just buy the stem cells. And of course, they are commercial products, so they are compliant with all the requirements.
And then I guess there's something else that comes up. I mean, it comes up a lot actually in the context of generative AI, funnily enough, which is the lack of any arrangements in relation to the ownership and commercialization of results. Again, is that something that you think about at all?
I'm not sure. What do you mean? Arrangement?
Well, so in generative AI, a lot of generative AI is built by essentially ingesting the internet. No one sought permission to do that. People are, I mean, no one's really making money off it, but in theory, you could be making money off it. And there are interesting questions that come up about whether that is okay or not.
Yes.
So in this case, if you're building something that is profitable from donated stem cells, I'm just wondering what the ownership and commercialization of your results looks like in that context.
It's very interesting. I never thought about this. No, I don't think that people who gave the cells should own the results. I don't think it makes sense because they have no contribution. You can always take from someone else. I don't think so. I honestly think that sometimes the ownership is exaggerated. Okay, I understand when you take the art pieces to teach the AI. In this case, okay, this is a question about ownership. But if you just take the samples, biological samples, I don't think the donors should have revenue because they already sold them. So basically, if you agree to give your skin, you agree to give also the outcome. And I generally think this is fair because they get this honest deal. I mean, you give your cells, you get the money, and so I don't think they should claim any ownership, honestly. But it's a very interesting question. Nobody asked this, so I don't know. Maybe one day will arise, but I think it will be relatively easy to solve.
Okay. You talked about, you used the word stress in the context of cells on electrodes. Can you unpack what you mean by stress a bit? I guess my question really is, can your biological systems suffer?
Yes, well, suffer is not the right word. I think suffer is something more complex because we have brains. But stress, biological stress, can be observed by anything from single cell to complex organism. And stress means any aberration from the homeostasis. So, for example, if you have these are experiments I did actually during my PhD. You have living neurons in the lab. You put them something called LPS, which is lipopolysaccharide, which is a complex name for something which is cause inflammation. Then you induce stress. That means they will start to produce pro-inflammatory molecules. So there is a lot of, and actually anything can cause stress of the cells. But I wouldn't say it's related to suffering. I think suffering in this case would be, how you call it, the anthropomorphization, that, that you believe, but it doesn't mean they have feelings and they are suffering. But yes, definitely stress in every biological item occurs, also in plants, in anything what is living. And actually, I don't know if you can call stress also for dead matter, but that's outside my field.
Yes, it's interesting to me, this, because instinctively, I've always rather liked, I use the word suffer because there's an English philosopher, Jeremy Bentham, who argues with respect to the moral status of animals that the question is not can they reason or can they talk, but can they suffer?
Absolutely. This is very interesting. And actually, this line of thinking is, I think, causing a lot of troubles because people associate this human feeling in everything. But, we have to respect philosophers. Of course, they spend a lot of time thinking about this. But yes, you are right. But actually, it causes a lot of problems, I think, especially in the perception of biocomputing, because people associate these human traits in our living neurons, which I don't think it's right. But yeah.
Well, I think so maybe there's another question then, which is, given our limited understanding of consciousness, how do you quantify when a neural system is displaying a trait that maybe requires moral attention?
You absolutely cannot do this because there is no scientific way to measure consciousness. And actually, philosophically, this is what I heard from philosophers, that the only consciousness you can be sure about is your own, because you cannot measure this even in other people. But it's open question. So for philosophy, it's very difficult question. And actually, this is why I should mention this. When we talk about philosophy, we actually reach out to philosophers because we ourselves are not competent. We can elaborate, but it's not really competent elaboration about philosophy. And we reach out to real philosophers to help us to answer all these questions. Although I can tell you, consciousness is more for general public. Real philosophers, they more think about the relationship between technology and us, how it's changing. But yes, consciousness is also open and topic. And when you look in Wikipedia, you can see there is 100 years of research, and there are all spectrums of opinions, from that it doesn't exist to that it is everywhere. So yes, so it's very open and no way to measure scientifically. So that's why it's so controversial, yes. But we hope philosophers can help us with that.
That's super interesting. Thank you. Slightly off topic, actually, but I was just thinking, obviously our understanding of our own brain and how it works is pretty limited still. We understand bits of it, but there's a lot we don't understand. So do you think the work that you're doing might inform a greater understanding of how our own brains operate, and might lead us to, more treatments for mental health type conditions and those sorts of things?
Oh, yes, absolutely. In many ways, I believe our research can contribute, although it's not our objective, but a side effect. Like in every deep tech project, you have kind of like side effect, which you didn't aim for, but you get some technologies, some solutions which are like side effect of your research. Yes. Like, for example, understanding learning in vitro, it would be a huge revolution also for medicine.
Yes, thank you. Is there any question that I've not asked you that you would have liked me to have asked you?
Well, what I could add is where people can find us, which is, I would recommend highly to check our website, FinalSpark.com, which is a great repository of information about biocomputing. And I think people can decide how they want to, if they want to interact with us, they can send us a message, they can subscribe to a newsletter, they can join a Discord. So all is on our website, and we give a choice depending if you are, journalist, or you are general public person, or you are scientist or investor. And there are different ways you can engage with us, and we are open for discussion with everyone. So yes, so I would highly encourage to check our website.
Brilliant. We'll include a link in the show notes. And are there any sort of books or papers or anything that you recommend if we've sort of sparked anyone's interest in the subject?
So I would definitely recommend our own paper, which you can find on our website. This is the only paper we published because we are a private company, so we don't really do academic career, let's say, but we have published paper about our lab. And so everyone who actually is interested in the field of biocomputing, maybe to work on this in the future or even now, that's a good starting point, because the paper gives the foundation, what you need to know actually to work in the field. That you need some biology, of course, you need some engineering, but in the paper you have exact examples of what do you need to be able to work in the field. So I think it's very useful. I always recommend this to our, for example, future interns, but anyone actually could read it, anyone who is technical. And for the books, I don't know any book. So far, I think this is too new topic. I could recommend our blog articles on the website. I think in such a new fields, it's more likely you find some articles, not really full books on the topic. At least I'm not aware of that, but if anyone knows, of course, is welcome to send us the link. But I've never heard about the book specifically on biocomputing.
That's fantastic. Dr. Ewelina Kurtys, thank you very much indeed for joining me today on the GOTO Unscripted podcast.
It was a pleasure. Thank you.
Thanks for listening to this episode of the GOTO podcast. Head over to gotopia.tech to discover lots more content from the brightest minds in software development.